Okay, so in the last video I was cut off at the last minute. So the one thing I kind of want to talk about is, go back to is, where is it? Okay, there we go. Is essentially going over the easy ANOVA function again. So really quickly, the assumption that I mentioned that I was going to be looking at is sphericity, and just to go back over what sphericity is. In the previous video I talked about it, but I'm going to talk about it here again. So sphericity is a less restrictive form of compound symmetry, and the way that you would calculate sphericity, or the way that it would work, is if you had your different conditions, you calculated, you got all your scores, and then you would calculate the differences between the scores in each condition. The difference in variances in those scores, according to the assumption of sphericity, should be roughly equal. So that's essentially what sphericity is. Here, the Mauchly's test is incorporated into the easy ANOVA function. So that's pretty sweet. So what we see here for sphericity, looking at our p-value, we have actually met the assumption of sphericity, given that our p-value is greater than 0.05. Our p-value here is 0.70, so 0.707, so rounding up to 0.71, so we have met sphericity. However, if we have not met sphericity, then we would have to go towards looking at our Greenhouse-Geyser correction and our Quinn-Feltz corrections. But I do mention, if the estimates are greater than 0.75, then we would look at Quinn-Feltz corrections. However, if they were less than 0.75, then we would be okay with the Greenhouse-Geyser. So it's just really important of looking at your estimates and making sure you look at everything with your data. Now that we're done looking at sphericity, let's see what we have here. And we actually don't have anything important. Well, I'm not saying important, but significant. So here, I pretty much just like rounded this, because even though I know it's greater than 0.05, I still think it's always an easier way just to show it rounded out. So rounding, it is 0.128. So this means that we don't have a significant effect of, there's no significant main effect of lighting on attractiveness ratings. However, if it was significant, then we would say otherwise, and we would look at our sum of squares. We look at the residual sum of squares, and all of that good stuff to determine and essentially break down our variability with our groups, or with our experiment, to see how much of our experiment explains like such effect. So that would be really cool to look at, if we had a significant effect, but we don't. So boo. Anyways, now if we did not have a specific prediction, and I didn't, then we would have to use a post hoc test. But I do want to stress the importance of creating or generating a prediction, because you don't want to just say, oh, I just put this experiment together, I don't have a specific hypothesis, let's just throw something out there and see what we can find. You don't want to do that. Well, it's up to you what you want to do. I'm not the person living your life. You are. So you do what you want to do. But I do want to stress the importance of creating predictions. Yes. So if we did not have a prediction anyhow, then we would use the pairwise t-test as a post hoc test. And specifically we specified Bonferroni. So, in looking at our conditions, specifically three conditions though, we would notice that not 3, 4. Jesus Christ, I'm blind. Anyways, so as far as bright and normal, nothing there. Nothing there for dim, normal, or dim and bright. Dark and normal, there's nothing there. But for dark and for bright lighting conditions, there is something here. So this is kind of neato, not neo, neato. So essentially there is some form of effect, or well, not some form of effect, but a difference is what I would like to say. A difference in comparison of comparing like dark to bright. So that's low-key cool. Yep. And this is just the summary attractive model here. All this cool stuff. And gives us our t values and our p values. So as far as significance goes, nothing is significant, however. But once again, I do want to stress this is fake data. I'm pretty sure there's somebody out there that would like to study this form of this experiment, or essentially a research design like this experiment. Stressing this is fake data for that one person. Do not go out and say it has an influence. Well, lighting has an influence on attractiveness. I don't know that. Just want to throw out there, this is just fake data. If you want to do that, if you want to test that out, that's on you. But you cannot use this video as a form of conclusion. I want to stress that for that one person, because there's always that one person. I believe I stressed that in the second video. Not the second, the previous video. But I'm stressing it again. Okay, so now, even though I did not have a specific prediction, if I did, then I would have to do a planned contrast. So a planned contrast would allow me to dive further into the analysis and essentially look at and compare different groups to one another. So the thing that you want to do, you want to set your weights and then combine them together. And then you do all the, well, you really do all this lovely stuff here. No, don't move. So that's pretty much for a planned contrast. This is the coding for it. So now another way that you can look at, another way essentially that you could have done an one-way repeated measures ANOVA is through a multi-level approach. So essentially this is using the multi-level linear model with the LME function. So you would just do these commands. If this is what you wanted to do, you could use these commands here. And then you can follow up with a post hoc test. Yeah, buddy. And then with your summary. That's pretty much it. Now we're going to move into our effect sizes. And our effect sizes are essentially to what magnitude does lighting have on attractiveness, or as far as strength. So these are the commands that you would run. I'm going to run these. Well, let me back up really quickly. So the effect size, as far as what we've done, up here, not up here, on the console, silly. Okay, so as far as effect size goes, we would consider this as our effect size. So really looking at it really quickly, 0.188 So rounding that up to 0.19, that's not a very big effect size. It's fairly small, but you know, what can you do? It's data. This is fake data, by the way. I'm going to continue to stress that. So we do have a small effect size here, but if you were to do your contrast, or essentially use the LME function specifically, then you would have to run these commands here, and then using the t values and the degrees of freedom values in that summary attractive model that we have here. So just scrolling up really quickly, using these values here, not these values, these values here, then you can run your contrast, not contrast, you can calculate the effect sizes for your contrast, comparing, like, not comparing, but for your, what is it? For your bright, your dim, and your dark, and you can compare those. And that's pretty much it, you guys. So going quickly to the research web document page. So kind of just to sum up our findings, even though we've had our descriptive statistics, our box plot, and our bar graph, in looking at those things, there was a sense that possibly dark lighting had the greater mean. There was a greater attractiveness rating for the dark lighting condition. I could not get that out for some reason. I don't know. My brain is being weird today. Anyways, so that's pretty much what we found with our descriptive stats, our box plot, and our bar graph. But when you get into the nitty-gritty of the ANOVA, there was no significant effect of lighting on ratings of attractiveness. I do want to stress that correlation is not causation, or there's no implication of causality here. That's just an easy way for me. I feel like that's the easiest way for me to get out what I'm trying to say. But with this video, I'm not implying that there is a causality here. And then with our sphericity test, and I included this just for personal reasons. Kind of feel like I want to give the whole story. The Maltese test indicated that the assumption of sphericity has been met. So that's pretty much how it goes. Now, really quickly, I do want to talk about the assumption of independence, because I did talk about that before. Backing up really quickly, we have met the assumption of normality, but as far as independence goes, there is a potential flaw that I see here for this specific design. Whenever you're using the same person for a specific for each condition, if you're using the same object for each condition, like people, let's say there's participant 1 is looking at the object that we're rating for attractiveness. If they continuously to look at that person from normal to bright to dim to dark, that can impact their observation of them, and maybe that might be the whole point. But depending on what you want to do, if you're trying to be as objective as possible, that would kind of be a very big flaw in the plan. So it's very possible that the scores do influence one another. So you take this with a grain of salt. And so that's pretty much it for my video. Thank you for watching. Bye.